So today's session is to gain confidence. Confidence on what? Confidence on understanding the what is impedance and what is the Q factor, what is the resonance. Okay, so this part is very important. Okay, high scoring part of this. So okay, let's start. So AC current, what's basic? Basic is that current is varying with time. Current is varying sinusoidally with time. Okay, so and also voltage is varying. So current is coming once we are having the varying voltage, right? Okay, so what about the omega? This is the angular frequency. And what about f? Relation between omega and f? Omega is equal to 2 pi f. Okay, time period t. So what is time period here? Time to complete one cycle. So there is a two cycle, right? Half cycle and half cycle. One to time required to complete one full cycle. That's called time period. Okay. So time period and frequency inversely related 1 by f, right? Now phasor diagram. So phasor diagram is actually we are just presenting the phasor, the vectors like the voltage vector and the current vector, right? So it's a geometric entity. Phasor is a geometric entity, and we are analyzing the alternating quantities. What are the alternating quantities? One is current and the three voltage VL, VC, and VR, right? Okay, so this is VL, VC, and VR. So we know that VL is the inductor, the load or voltage drop that is leading on current, and VC is the voltage drop on the capacitor. So current is leading the VC, and VR and the main current are in the sync, they are in phase. Okay, and this is the relation. This is the resultant voltage is equal to contribution from all these three voltage. Okay, and VC and VL are in opposite phase and opposite. Okay, so let's go to the next slide now. Okay, fine. So this is the impedance triangle we have. So this is impedance, this is the resistance, and this is the XL is the inductive and the capacitor. So XL minus XC. Why it's coming? Because they are in opposite phase. I already told you, right? Next is LCR circuit. So LCR circuit in series. Okay, so that means resistance, inductor, and the capacitor are in series, and there is a voltage source, the varying voltage source E0 sin omega t. Fine. So for the resistance, the voltage drop is VR, and VR is in sync with the current. That means they are in phase, no phase difference between them. And for the inductor voltage, VL is leading the current with pi by 2. So VL is the leader, right, leading the current. And in the capacitor, current is leading the VC. That means VC is lagging behind the current pi by 2. Okay, so lead and lag, these two are the new terms here. So you have to make it and socialize so that it will help you, and it will help you to the complete the chapter in a shorter time, and you can remember the things by making a daily culture. Okay, fine. Now let's come to the point, the resonance. So before going to resonance, we have to understand this relation. The current I0 is equal to the voltage drop divided the total impedance, voltage and total impedance. So total impedance is R square plus XL minus XC square. So three contributor. This is R, this is the XL, this is the XC. Three contributor. So if you earlier, if there was no inductor and capacitor, it was purely resistive. Now resistive, inductive, and capacitive. So XL and XC. So XL is the resistance due to the inductor, and the XC is the resistance due to the capacitor. Right? Three of them is working together over here. Now resonance means what? In these equations, I need the maximum current, and that's the resonance. So I need the maximum current. I will be doing the tuning. Maybe in TV set or radio set, I am doing tuning, and I am reaching a frequency where XL and XC opposing each other. So the net result between XL minus XC is 0. Okay. Now what's happened? Like I need the maximum current. That means impedance should be minimum. It is in denominator, right? Mathematically. So to make the impedance minimum, I have to make this part 0. That means XL should be is equal to XC. So capacitive and the the reactive inductive reactance, that they should be equal, so that the contribution will be 0 and current will be maximum current. So in this maximum current, that is the resonance condition, and that frequency is the resonating frequency. So current maximum means impedance is minimum, right? Okay. Now, very important slide this one. Okay, I will explain you over here. Right. So, what's happened? The resonance, we understand resonance means a particular frequency where current is getting maximum. Okay. So, in the resonance, now we understand, we are going to understand the Q factor. So, Q factor is, is measurement of the sharpness of the resonance, right? If you see, so let's understand what is Q factor. Q factor is an, quantity which is the ratio between the voltage across the inductor or the capacitor divided by the applied voltage. So here I0 WL. So W0L means W0 is the resonating frequency, WL is the inductive reactance, I is the current, main current, divided by IR. So it's becoming W0L by R. From here we are getting, so W0, we already know that W0 means 1 by LC. From where we get, when we are doing XL is equal to XC, we are getting W0 is equal to 1 by root over of LC. Okay, fine. So this is the expression of the Q factor. Another expression of the Q factor is resonant frequency divided the bandwidth. So resonant frequency is omega 0 and bandwidth is omega 2 minus omega 1. So 2 delta W. Now what is 2 delta W? So W1 and W2, this one, like, here the current is reduced to 1 by root 2 part. Like if main current is maximum is I0, so in this particular frequency, the current will be I0 by root 2. So these two are the frequency omega 1, omega 2, and that here we are getting the bandwidth between this one is the bandwidth, right? So 2 delta W or omega. Okay, so this is resonant frequency. So bandwidth, whenever there is a sharp, sharp increase in the current and the sharp decrease, like, look at here, this is the steepest graph. So in the here the maximum current we are getting, on that time the resistance will be low. The lower resistance we are getting maximum current, definitely, because R in the denominator. So R, the more R will be, the lesser we will be getting the more current. Okay, so graph is steep. Now this is a flattered graph. Here you can see this bandwidth is getting increase in the flattered graph. Okay, that means here if I change the frequency, the current spike will not go that level. But here we change, we are just tuning the frequency. In a particular frequency we are getting maximum current. In the next frequency is sharp drop. Okay, so in the frequency change near about this, so we are getting a sharp decrease in the current. So that is the sharpness of resonance, and this is the utility of the Q factor graph. Okay, so I think that's it for today. Next class I'll come with some more. Okay, one more thing, the resonance frequency, how we are calculating. We are calculating like this: the resonating frequency I0 is equal to E0 by Z, right? So this is the impedance. So I have to make I max, that means Z will be minimum. To make the Z minimum, I have to make XL is equal to XC at resonating frequency. So we are getting the relation, right? So just do practice this one. Okay, and so here, what are the utility of these things? Resonance we are using in the tuning of the circuits, like for day to day for the TV circuit, right? And for the radio we are using the resonating frequency. So resonating frequency F0 is equal to 1 by 2 pi LC, right? So this is the derivation we have. As I already told, XL is equal to omega L, XC is equal to this. So if you are equalizing in the resonating frequency, we are getting this particular term. So this is the derivation part of this one. Okay, so that's it for today. So next session I'll come with the more details on some numericals on this part. Okay, thank you.